Hello viewers, I hope that you people are watching my video lectures. So in the last lectures we gave the content discussed on fluids, properties of fluids, hydrostatics part 1, part 2, then hydrodynamics. Then now we are going to discuss in this session the topic called surface tension, a very important topic in physics. And this is J. Murugesan, physics faculty from E for U, and we can go for subject discussion now. Now this is the content sheet for today's theory part, surface tension theory part content sheet. These are the contents what we are going to discuss in order. Okay, so first we are going to discuss a type of intermolecular forces. Yes. Now in properties of solid, there we introduce the the concept of interatomic and intermolecular forces, which is responsible for different states of matter, solid, liquid, gases. And I hope that you watch that video and you may get the idea about that. Now you please come for the discussion. In intermolecular forces, there are two kind of force we can say that. One is called as a force of cohesion and another one is called a force of adhesion. So in this force of cohesion, you just see that it is the force of attraction. So now we will start that. The first content is intermolecular forces. So intermolecular forces. So okay. So what is cohesive force means? Cohesion. So cohesion means the force of attraction between the like molecules. Attractive force between the like or similar molecules or similar substances. So similar molecules. So similar molecules. So that is called cohesion or force of cohesion or cohesive force. Example, the force of attraction between the two liquid drops or water drops. Okay. Now you see that the second kind of force is called adhesion, force of adhesion. What is this force of adhesion means? It is the force of attraction between the unlike molecules. Like for example, you just see the picture, we can see that the water droplets on the grass surface. So grass molecule is different and the water molecules are different. So there is a force of attraction. So such type of force of attraction between the different type of molecules, that is called adhesion, force of adhesion. So this is for a force of attraction between the different or unlike or dissimilar molecules. So that is a force of adhesion. So next we can go for the another one, that is molecular theory for the surface tension. How the concept of or the property, basic property for a liquid surface tension arises means, you just see this first diagram. I am considering, you are just considering the three molecules. One is at the very near the bottom of the container, and another one is very near, just above that, and the third one is very near the or below the free surface of the liquid. Just to see that the center molecule, so this is the center molecule, what is there? So this is the center molecule, and you just see that center molecule is there. In this center molecule, this is surrounded by a neighboring molecule, a similar kind of, as for example, if you are considering water, then this particular water molecule is surrounded by, this particular water molecule is surrounded by the neighboring water molecules. That means this particular molecule experiences the force of cohesion by the surrounding molecules. So by seeing this picture, we can say that the force of attraction for this particular molecule is exists up to a certain distance. The corresponding distance is called molecular range, and this form a three-dimensional structure, a sphere, that is called a sphere of influence. Now you see that similarly, therefore since this particular molecule, say for example this is molecule A, this particular molecule A experiences the net force due to the total force acts on this particular molecule A is 0 because it experiences the force in all directions, therefore the resultant will be 0. Similarly, you consider the second molecule, say for example this is molecule B, then we can say that the similar explanation here also. The total force act on this particular molecule B also will be 0. But now you come to the third molecule, which is near the free surface of the liquid. So that for free near the molecule which is near the free surface of the liquid, it experiences the force of cohesion by its neighboring molecules. But you see the diagram for the clear understanding. This particular molecule, say for example molecule C, this experience the force as shown in the diagram. This is the interface, this is the air or yes, gas, and this will be liquid interface. So in this free surface there is no as molecules for force of cohesion. So because of that reason, this particular molecule C, these forces gets cancelled out, so therefore it experiences only net downward force. So that is the main conclusion. So whenever a molecule is taken from the bottom of the container to near the free surface of the fluid, the total force acts on the molecule is gradually increases, and when it reaches the free surface of the liquid, then there is a net downward force. This downward force results the property of surface tension. Now you please see this diagram, second diagram, which shows the clearly how that resultant force acts on that on a molecules which are near the free surface of the water or liquid exist. So due to this what is that attractive force, the free surface of the liquid is just acts like a stretched membrane. That property of this liquid is generally termed as to be surface tension. So these are just introduction about the content. Now you please go for the surface tension. So in this surface tension, the definition is symbol is T. It is a force per unit length. So unit is Newton per meter and the symbol is T. So it is a force per unit length, or from this I can say that yes, a force due to the surface tension, that is F is equal to TL. Yes, the SI unit is there. So this is Newton, that is a meter. So Newton per meter. Now we go for the another slide. Now you see that. So this is the force due to the surface tension. Here you must keep one thing in mind, that is for liquid drop. So this is the liquid drop. Inside that what any liquid is there, it has only one free surface, because this boundary of the liquid surface in contact with the air, therefore it has only one free surface. Therefore in this case the force due to the surface tension is F is equal to TL. In case of air bubble or soap bubble, so soap bubble, just see that this is the soap bubble. So this is the film layer, says the soap film layer. So because of that reason it has two air layers. So here also air is there, here also air is there. Therefore it has two free surfaces. Therefore the force due to the surface tension for this case is F is equal to 2 times of TL, because it has the two free surface. This is a very important thing what we must keep in mind for the further discussion. Now we see the diagrams. Yes, there are different systems given. The first diagram shows that there is a needle which is floating on the surface of the water. You just see that. So when the needle is floating on the surface of the water, or you can see that some insects are walking over the surface of the water. So in this case, so yes, just to see the first diagram there. So this is the needle placed on the free surface of the liquid. So this is the direction of surface tension. So the force due to the surface tension. So this is force F. So this is force due to the surface tension F, which acts tangentially to the contact point. So this force is resolved as a component. This is a theta, and this will be resolved as a component. Now we see that there is a net upward component. Say for example, according to this diagram, we can say that this will be F cos theta and this will be F sin theta. Okay. So here also the same thing, we can say this will be theta, and this F cos theta component gets cancelled out. These two are equal and opposite. But there is a non-zero component along the vertical direction. So therefore in this case, how the needle is balanced on the surface of the water is that W is equal to mg, weight of the needle is acting downward, whereas the component of the force due to the surface tension F sin theta is acting upward direction, which balance this. So therefore I can say that here 2F sin theta, that is equal to mg. So this force balances the weight of the needle, that's why it is floating. This is the explanation for the first diagram. And similarly you just see for the second one. Yes, if you want to take the needle out, so the needle is floating on the surface of the water. If you want to take it outside, we must do the we must exert or apply some force F as shown in diagram. Just to see that when you are taking down, so when the needle is taken as outward, so this is the force of due to the surface tension whose component is acting downward, so that is a TL, and this force is also TL. Now the total force in downward direction is 2TL, and meantime the weight of the needle also acting downward, that is W here. Therefore the total downward force acts downward is W plus 2TL. So if you want to lift this needle from the free surface of the liquid, say this is for example F external, then the total force what we must apply is F external is equal to 2TL plus weight of the needle, that is mg. So some cases if you are considering the total external force to remove that or lift that needle. Now we come for the third diagram. This is annular ring which has the two free surfaces. So two free surfaces, that means this is the inner one and this will be outer part. So since surface tension is defined as force per unit length in the form of a circle, that L is replaced by circumference. Say this is a radius R1, R2 for example, and this is R1, that is our convenient. So force acting on this one is F is equal to, say for example F is equal to, or F1 is equal to T into, that L is nothing but 2 pi R1. So therefore 2 pi R1. Here that is taken as to be R2. Now you see that for this surface. So for this surface I can write the same thing. Here say for example F2, that is equal to T into 2 pi and that has to be R1. So this is the force acts on the annular ring. If you want to lift the annular ring, along with the weight, the additional forces is T into 2 pi R2 plus T into 2 pi R1 should be acts on that. Say this is for example, so this is for example F2 and that has to be F1 for this. So therefore we can say that the total downward force is W plus T into 2 pi R2 plus T into 2 pi R1. So if you are applying the external force which is equal to that value, then only you can lift the annular ring which is placed near the surface of the liquid. The same manner this is for circular ring and that is for circular disc. In the case of circular disc, it has only one free surface, that is the outer boundary, because the inner radius becomes to 0. Therefore in this case I can write that the force required, the net downward force due to the surface tension is downward forces, that is T into 2 pi R, or you can take either small r or capital R. The downward force acts on that one is this one due to the surface tension, and weight W equal to mg also acts on this. Therefore if you want to lift this object, the F external should be equal to W plus T into 2 pi R. In case of the very thin ring, we can say that R1 and R2 are merged together. Therefore we can say that it has the two thin ring. This is the thin ring which has the two nearby radiuses. So R1, R2 are very closer. Therefore we can take that as to be approximately R. Therefore the total force acts on these boundaries are same as to be the T into 2 pi R, and here also that is a T into 2 pi R. So in this manner we can calculate what is the force required to lift the object or from the free surface of the liquid, or the force due to the surface tension acts on that solid substances. And another one is surface energy. So surface energy and work done is there. So we must do some external work done. So let us consider generally W is equal to force into displacement. So force into displacement dx. Multiply by length and divided by length, I can get that F by L, just now we defined that as to be surface tension. So T into length into breadth is nothing but area, dA. So for example dW, this is dW. So this is the work done to change the any liquid drop or air bubble from one radius to another radius. For example, we just see that a liquid drop of radius from R2 and some other new radius whose value is for example R plus dr. So if you want to do that, there is a change in area dA. So therefore what is the amount of work done? For this case is we must do that is given by dW equal to say this is d into dA, or the final radius is taken as to be like this. So from this radius to say R1, that is to some other radius r2. So this is from r1 to some other radius r2. Then the change in area or the total work done for this process to increase the size of the liquid drop or bubble, then the total work done is given by W is equal to T into as a change in surface area, since therefore 4 pi and r2 square minus r1 square. So this is the work done. So W is equal to T into 4 pi into r2 square minus r1 square. So this is the work done to increase the size of the bubble. Next, the another subheading given there is surface energy. Now you see that what is surface energy means. So surface energy. Just now we said that whenever a molecule should taken from the bottom of the container to free surface, the force acts on the molecule is increases in downward direction. Therefore, we must do some external work done against the downward force. So because of that reason, some external work we must do. That work done is stored as a potential energy. So therefore, surface energy is nothing but it is the potential energy per unit area. So surface energy is nothing but potential energy per unit area. We know that energy and work done both are having same dimension. So therefore, energy and work done. So dW by dA. So we can say that dW by dA, that is equal to T. Since the dimension of work done and energy both are same, therefore I can write that this has to be dW by dA also, but that is nothing but T. So from this we can prove that the surface energy is equivalent to surface tension. So this is the thing what we discussed here has to be surface energy. Next, go for the another one. Now we see that another very important concept for the MCQ point of view, that is nothing but n-drop problems. That is, there are two cases in this. One is a smaller n number of smaller identical drops can combine together to form a bigger one, or the second one is a heavier drop is splitted as a n number of identical smaller drops. So this is the main thing what we are going to discuss, and before that kindly note down the content. See that n-drops problem, yes. So now you see that in this case what we have to be consider is the volume remains constant. That is the first point. You just see that whenever n identical small drops are joined together to form a single larger drop, yes. In this case, the first point, this is n-drops problem. N-drops problem. So that is a very important thing, because the same thing is used in electrostatics also in capacitance topic. So now you see that the first point what you have to be keep in mind is the total area of the n identical drops, that is A total area for the smaller drops. N identical smaller drops is always greater than the single big drops area. That is the first point. And second point is whenever n drops is combined together to form a bigger one, or bigger one is splitted into n identical smaller drops, the total volume of the liquid is constant. So the volume remains the same. Volume remains the same. So because of that reason, I can say that volume remains same. Because of that reason, the volume of the big drop is equal to total volume of the smaller drop, that is n into V small. So therefore I can say that this is a 4 by 3 pi r cube, that is equal to n into 4 by 3 pi into small r cube, where smaller is the radius of the smaller drops. So because of that, we just see that we can get r cube, that is equal to n into small r cube, or from this capital R equal to n power 1 by 3 into small r. So this is the main results what we get. And the third point what we have to be keep in mind is, whenever smaller drops, that means whenever area is since the initial area is more, because the smaller drops are having total area of the smaller drops is more when compared to the bigger drop. So whenever a liquid drops, n number of liquid drops join together, coalesces together to form a bigger drop, there will be a release of energy. So therefore the energy released, that is equivalent to work done, because energy work done both are similar. Okay, so now you see that the work done or the surface energy released during this process is nothing but T into dA, what we said earlier. So that is T into the dA is nothing but area of the smaller drops, n number, total area of the smaller drops. So dA, change in area, is nothing but total area of the smaller drops minus total area of the bigger drops. So A big. So this is the relation. So therefore W is equal to T into, this can be written as n into 4 pi r square. So n times of 4 pi r square minus 4 pi capital R square. So therefore take these common terms outside. So 4 pi is T is taken, 4 pi is taken outside, the remaining term is n r square minus capital R square. So from this again you take the capital R square outside, then again I can write that 4 pi T r square is n into small r square divided by capital R square minus 1. So from this relation we can get that, as r by r. So r by r, that is r by r is nothing but 1 by n power 1 by 3, it is going to numerator n power minus 1 by 3. Now you just square the term. Yes, sometimes students may get the confusion here how the steps arrives. So for that reason I am explaining here. Now you square this term. So now you square, therefore r by small r, that whole square, that is equal to n power s minus 2 by 3 will come. Now I can replace this one by this quantity. So therefore I can write that 4 pi T r square n into, this value is n power minus 2 by 3 minus 1. Now you see that again n is there, n power minus 2 by 3 is there. So n power 1, n power minus 2 by 3, this can be written as 1 minus 2 by 3. Therefore you just see that n power 1 by 3. Therefore I can write the final result as to be W. So W is equal to 4 pi T capital R cube, R square. So this is the R square term, and what we are getting is just see this term, n and this term is there. So here a small r square by capital R square is there. So that can be written as to be n power 1 by 3. So n power 1 by 3 small r square by capital R square minus 1. Now again you take the just see the term. So now you just see the results what is given. So that can be taken outside, and r by so now you please take care of this, and this term actually that r square by r square only is replaced here. So please be careful with that. Therefore I can get that has to be n power 1 by 3 minus 1. Yes. So that is the thing what we get. So this is the another equation. So just to keep in mind, this is the one equation what we get in terms of surface tension. Yes. And another one is in terms of that the radius of the larger sphere, okay, or a larger drop. The same can be replaced. Now you see that during the case when the liquid drops gets when the liquid drops get, you just see that relation. So when the liquid drops gets combined together, during that process some excess energy is released. Because of that we may get that energy may be used, that work done or energy may be is used to increase the temperature of the liquid drop. Therefore, I can write that W is equal to S J into Q from the Joule's mechanical equivalent concept. But we know that, so the amount of heat energy required to change the temperature of the any liquid, that is J into that Q is given by S mc delta theta. So where m is mass of the liquid and C is a specific heat is capacity of the liquid. So therefore, by equating these two relations, so we can write that, for example, W is equal to is 4 pi T is we can write that 4 pi T R square into n power 1 by 3 minus 1, that is equal to J times of mc is delta theta. If you want, you can replace this m by the density. So because the density of the liquid is given by, the drop is given by, is mass is equal to density into volume, that is density into 4 by 3 is pi capital R cube, here the mass term. So by substituting these values and rearranging the term, you can get that results. So that is given for your practice. Now we go for the another one, is the same concept, the splitting of a drop, a single bigger drop into n identical drops. In this case, you just see that all the analogy is very similar. But what is the main difference between this case and that one is, here is the main difference. So now you see the difference. Now a single drop becomes to be n identical, n smaller drops, n drops. So in this case, the first point, as we said here, the total area of the smaller drops is greater. Therefore, A big is lesser than S total area of the smaller drops. Therefore, S a small one. And the second point, what we must consider is volumes remain same. So the same concept is here also true. Therefore, volume is constant. Volume remains constant. And the third, that same analogy. But what is the main difference between here and there means here energy is released. In this process, energy is released. But whereas here, that value, so in this case, during the bigger drop into smaller drops, we must supply the energy. So we need or we have to supply. So we have to supply the external energy. Supply the external energy to that. So that is the main difference between this and this category. So when coalesces or combination process, energy will be released because of the area changes. Here we need the external work done or external energy to split up the liquid drops. Suppose the external energy is not available, so the bigger drops takes its internal energy, then the temperature will be decreases. So the temperature will be decreases, T will be decreases. So temperature will be decreases, but in this process temperature will be increases. Here not only, so we come to here not only the temperature of the liquid is increases, some cases the same as excess energy is used for kinetic energy also. In that cases, for the coalesces process, the total energy released, that is equal to, sometimes we can write that is kinetic energy of the bigger drop. So kinetic energy of the bigger drops. So that is the main difference between coalesces process and splitting process. Now please go for the another one. The shape of the meniscus. We know that in different vessels, if you are taking a very wide vessel, we can see that the surface of the water or liquid is flat, that is a plane surface. And some other cases, burette, if you are taken that water will be a concave meniscus or concave as a shape. But in the case of mercury, that surface will be vex surface. So plane surface or plane meniscus, concave meniscus and convex meniscuses. How that arises and what is the reason for that we will discuss. Please note down this, children. See that another concept, the shape of the meniscus. So why different liquids in different vessel or yes, situations they are having different shapes? One is a plane surface and another one is concave and another one is convex. You just see that the first diagram, the surface tension acts on the free surface of the liquid gets cancelled out, and left and right the total force gets cancelled out. But you see the second diagram, since the diagram is given for the concave meniscus. For concave meniscus, this is the force. This is the shape of the meniscus and this is the liquid surface. Yes, in this case, the forces or surface tension is acts tangentially, and the force due to that also will act tangentially. Now you resolve that has to be a component. We can, as we said earlier, so the horizontal component gets cancelled out. There will be a net upward force. Yes, so that is the thing. That's why here we mentioned that there is a term called a pxs that we will discuss as a next as a topic, and how that things are having different shapes. Now you see the another one. That one is a convex meniscus. Convex meniscus. In this convex meniscus, we can see that mercury. So see that. In this case, the surface tension is acts in downward direction. Therefore, the component, non-zero component, which will act downward. To balance that, there will be a upward force that is called pxs. So there are three types of meniscus. One is plane, and another one is concave, and another one is convex meniscuses. This shape change arises because of the surface tension acts on the liquid. Now you see that as a concept of excess of pressure. That is the very important thing. You just see, yes, a plane surface, the concept of excess of pressure. So the concept of excess of pressure. In a plane surface, so this is the force. There is no other additional force due to the surface tension of the liquid. Therefore, that excess pressure on this system or surface will be zero. Yes, now you see that. But in the second case, what they mentioned in this, in the case of concave meniscus, the horizontal force component gets cancelled out, whereas this horizontal force gets cancelled out. This component of the force gets cancelled out, and this also gets cancelled out, but only non-zero forces are exist due to the surface tension. So this is the force due to the surface tension, and in order to balance that there will be excess pressure to act on this concave meniscus or surface to make the stable equilibrium condition. So similarly here also, this is the surface tension. This is the force due to non-zero force due to the surface tension which acts downward. In order to maintain the stability or equilibrium, the excess pressure is developed inside the liquid also. So therefore, I can say that in the case of a concave meniscus. So concave meniscus, this is the liquid, and this is the liquid, and a air surface. Okay. Now I can take this is P in, and this region has to be P out. Since in order to balance this force due to the surface tension, the additional forces acts over there. Therefore, in this case, P out is greater than P in. Therefore, there is a pressure difference between these 2 points or surfaces. That pressure difference is given by excess of pressure. Therefore, delta P, that is equal to P out minus P in, that is equal to 2T by R, where R is radius of the meniscus. So now you see the third one, that is the concave meniscus. So this is the thing what we completed. The next one is convex meniscus. In the case of convex meniscus, you just see that convex meniscus, it will be like this. So here is the force due to the surface tension. So this is the force due to the surface tension. So this is the liquid interface. Okay. So now this is P in, and this is taken as to be P out, and this is P in and P out, there we said. So in this case, in order to balance the force due to the surface tension, additional pressure or force is exist here. Therefore, in this case, I can say that P in is greater than P out. Their pressure difference delta P is nothing but P in minus P out, that is nothing but 2T by R. is given by r. Again this r will be the radius of the meniscus. Okay. So now you see the diagrams, there are different systems where we can write the excess pressure. The first one is called so excess of pressure, P excess in different system. P excess in different system. The first one is liquid drop. So in liquid drop, just to see that a liquid drop is nothing but which contains only one free surface. So therefore this is P in, and this will be P out. Therefore delta P, that is equal to P in minus P out, that is equal to 2T by R. But in the case of soap bubble or air bubble in so we see that in bubbles it contains two free surfaces. As we said earlier, it contains two free surfaces. So this is the direction of the pressure internal, that excess pressure acts on this. So here also in bubble it has two free surfaces. Here also air will be there, here also air will be there, in between liquid layer is there. So this is P in, and again this will be P out. So the direction of the pressure, excess pressure acts inside this bubble will be given like this. Therefore again we can write the delta P, that is equal to P in minus P out, but that is equal to, here it has the two free surfaces. Here it has only one free surface. So these two times of that is equal to 4T by R. But now we consider the third one, that is the diagram given here. This is the big liquid drop. Inside that some air bubble is exist. Now you see that in such type of situations, and now you see that here I can write. So the third one is that is called bubble inside the liquid, liquid or liquid cavity. So we can treat both the way. Okay. So in this situation, you just see the diagram for your better understanding. Suppose the cavity, that is air bubble, is in this region and which is near to the free surface. Now this is a P in and this will be a P out in this case. Since even though it is air bubble, this outer region, outer free surface is covered with the liquid. Therefore we can say that it has only one free surface. So because of that reason, so delta P in this case, that is a bubble inside the liquid or a liquid cavity, that is a 2T by R. Suppose the same bubble is some depth from the free surface of the liquid. So this is the free surface, the bubble or cavity is here. In this case, there is additional pressure apart from this excess pressure due to the column of liquid H. Therefore delta P in this case is 2T by R. Along with that, pressure due to the liquid column of height H, that is H rho G. These things we are already discussed. Okay, so that is the a case of excess pressure in the liquid drop, bubble and liquid cavity or bubble inside the S. Then the fourth one is there. So that is the fourth one. The next one is so suppose if we consider the liquid drop or liquid surface, you consider the liquid surface which has the non or unequal. So unequal radius of curvature. Say this is R1 and this will be like R2 is unequal radii. In that situation, what is the formula for delta P is, that is nothing but P excess is nothing but T into 1 by R1 plus 1 by R2. So you just take the general equation and use here in the liquid drop R1 is equal to R2, therefore we can get 2T by R. Similarly, the fifth one is a film surface, liquid surface. This will be the liquid surface, and next one is a film surface. So film of unequal radii. So in that case, we can get this things has to be R1 and this has to be R2 like this. So in this situation, what you have to do means you just consider two free surfaces are there. So therefore this equation can be rewritten here. This has to be delta P in the case of liquid film of unequal radius. Delta P is nothing but 2 times of this. Therefore 2T into 1 by R1 plus 1 by R2. So this is the concept of excess pressure in the various system. That means as a plane surface, concave surface, convex surface, that means meniscus, liquid drop, bubble inside the liquid, that is nothing but liquid cavity. The same thing is certain depth, and this is the unequal liquid surfaces, unequal film surface. Kindly note down the theory, students.